Okay, we're going to continue on here, chapter 16, acids and bases. Now that I found the file wherever it went, I'm not sure, but we're talking about acids and bases here, our second to last chapter here in chapter 16. So let us get into it. So let's talk a little bit about acids and bases. So acids were first recognized by their sour taste. Things like vinegar, which is main components of acetic acid. Things like citric acid, obviously, and things like lemons. Bases, on the other hand, have a very bitter taste, and they feel very slippery. A lot of soaps and like drain cleaners and those type of things, those things are all bases. Bases are sometimes referred to as being alkaline, and that's why, as we'll talk about, when you kind of see the word alkaline, it really does mean basic. If we think about sort of group 1 and group 2 on the periodic table, those are your alkali metals, your alkaline earth metals. So group 1 and group 2 on the periodic table, when they do have hydroxide attached to them, is where a lot of our strong bases come from. So a lot of those strong bases come from those two groups, especially if they have hydroxide in them. Things like sodium hydroxide, potassium hydroxide, kind of hang right over there to calcium hydroxide, come on down there to strontium and so forth. So a lot of these guys will be strong bases, and they will definitely have hydroxide in the actual formula. Now, sort of first sort of definition of acid and bases was done by a guy named Arrhenius. He did a lot of work with electrolytes, and as we talked about, electrolytes are things that when they do go for a swim, they do break apart into ions. They're able to conduct electricity. And basically he defined an acid as something that's able to produce the hydrogen ion in solution. And he defined a base as something able to produce hydroxide. So what we're talking about here is sort of on the product side there of a reaction. Those things get produced. And what that means in solution is you have free H plus, ROH minus floating around. So something that has the ability to do that, basically generate H plus, ROH minus. One really important thing about sort of H plus and acid-base chemistry is H plus and H3O plus are pretty much the same thing. So H plus, which is the hydrogen ion, and H3O plus is the hydronium ion, which is a polyatomic ion. They are used interchangeably. They're used interchangeably both in equations. They're also used interchangeably in formulas as well. So personally, I use H plus most of the time. So anywhere I put probably H plus, you can pretty much exchange it out for H3O plus. It's basically the same thing in acid-base chemistry. Hydroxide OH minus is typically obviously always used for bases. So how we make some of these things, again, we take something like hydrogen chloride gas there, dissolved in some water, we get hydrochloric acid. A reminder that acids, as we talked about when we talked about naming, typically will have the aqueous symbol next to it to indicate that it is an acid rather than a hydrogen chloride gas like it is over there. Also a reminder, as we talked about, right, if it does not have oxygen, the acid, it is hydro something acid, like hydrochloric acid here. If it does have oxygen and we're going to name it, it will have one of those polyatomic ions, will either end in ate or ite. And then if it ends in ate, your acid will end in ic. And if it ends in ite, your acid will end in OUS, like nitric acid. So that's nitric acid because that is nitrate as opposed to nitrite in that guy, which is nitrous acid. So a reminder that when you rename acids, it is all about the oxygen, whether or not it is there or not. And remember, it is only the ones with no oxygen that gets the hydro in front of the name. So it was a good step forward, sort of this early idea of acid and bases. It was limited as he did a lot of work with strong electrolytes and strong bases that contain hydroxide. As we'll talk about, not all bases will necessarily contain hydroxide in its formula. There are bases that can actually produce hydroxide and not actually have it in its formula. And those are a lot of times more of a weak base. So for example, you could have something like a weak base, which is ammonia. And ammonia, when it reacts with water, will produce NH4 plus and some hydroxide. So something like that, ammonia here, which is a weak base, it clearly does not have hydroxide in the formula, but it is able to produce hydroxide, so it is still considered a base. It is considered a weak base, as we'll talk about as we go through this chapter, different than, say, sodium hydroxide, which is a strong base, because sodium hydroxide pretty much just needs to go for a swim, and it will separate into its ions as it's a strong electrolyte, and it will produce a hydroxide ion really easily. Well, ammonia's got to go find some water, do a little bit of reaction to produce a hydroxide. So that is, again, sort of the difference between those. But they're both considered bases because basically they both basically can produce hydroxide. So when we talk about acids, just to kind of step back for a second, when we're talking about that difference between H plus and H3O plus, and that they are really the same thing, we can represent an acid dissociating or breaking apart by this type of equation here, where we take some HCl and basically it'll break apart into H plus and Cl minus. Remember that when we're talking about acids, the cation's always the H plus. We could also represent this same sort of dissociation in water with HCl plus some water. And if we do that, what's going to happen in this case is we actually will produce H3O plus, as the acid will send the H plus over, and we will end up with Cl minus. So both of these equations are essentially equivalent to each other. And in this case, we didn't include water in the equation, so we get H plus. Here we did include water in the equation, we get H3O plus. And again, they're both represent basically the acid part of that solution. And that's why they're basically the same thing in this consideration. Any questions on that there? And by the way, in terms of the base here, the water is actually sending the H plus over to that guy. So let's talk about really a more sort of general definition of acid and bases, and really sort of the definition that most people think about when they are dealing with acid and bases. And that's what's sometimes referred to as the Bronsted Lowry definition of an acid and base. And the Bronsted Lowry definition of an acid is something that will donate a proton, which is an H plus. By the way, an H plus is also referred to as a proton in acid-base chemistry. And that is because, as you know, hydrogen has one proton and one electron, and it does not have a neutron. So in order for it to become positively charged, it has to lose an electron, which means it's left with just a proton at that point. So that's why it's sometimes referred to as a proton as well. So we kind of represent and kind of name the sort of acid part of the solutions when we're dealing with acid bases, sometimes in three different ways. We sometimes talk about a proton, we sometimes talk about the hydronium ion, and we sometimes talk about the hydrogen ion, and they're all basically representing the same thing, which is really just the acid part of it. So in the Bronsted Lowry definition, again, an acid is something that will donate an H plus, and a base is something that will accept an H plus. And the important part of that is actually the positive part of that. And that is something that people mess up on a lot when we look at these things. It is not just a hydrogen, but it is also the plus, which means the charge of whatever you're dealing with does change. So you do have to adjust it based on the charge. So obviously, if you gain a H plus, you become one more positive, right? And if you lose an H plus, you become one more negative. So the charges of certain things do change as they lose or gain that H plus. And again, sometimes people focus more on just getting either adding or removing the H, but we do have both of those things happening. So taking a look at the general reaction here, If this is an acid, and this is just a generic sort of formula for an acid, it could be anything like HCl, HNO3, whatever it may be. What's going to happen here is our acid is going to donate its H plus over to the water. And in this case, the water would act as the base in this particular case, as it will accept the H plus. The sort of consequence of the Bronsted Lowry definition is it will create sort of partners on the other side of the arrow. So we usually will always have our acid and bases on the left-hand side of the arrow or the reactant side, and then they will have partners that they sort of create on the other side that they're related to. So let's take a look at what things that might be related here. And it is this guy here, the HA and the A minus. And on the other side, the A minus is what is known as the conjugate base. And the water and the H3O plus are related to each other. And on the right-hand side, the H3O plus is referred to as the conjugate acid. So it sometimes creates what is sometimes referred to as conjugate acid base pairs. Now, the only difference between those two, and the only thing that there can be in terms of a difference for them to be partners and related to each other, is this guy right here. It can only be one H plus difference in order for them to be partners. If there's anything more than one H plus difference, then they technically are not acid conjugate base pairs or base conjugate acid pairs. It has to just be that. Since the acid loses an H plus, the conjugate base will have one less H plus. And since the base accepts it, it will have one more H plus. And again, that can be the only difference and should be the only difference between them. So if there's something that is more than one H plus, if there is something that is more than an H plus and some type of other element, then they are definitely not related to each other. Any questions on that there? So if we take a look at sort of the water breaking apart, or the hydrochloric acid breaking apart in water, once again here, our acid is going to be this guy. Our base again is going to be the water, as the acid should send the H plus over to the water. Again, the result of that is our HCl and our Cl minus here will be partners, conjugate base. And our water and our H3O plus will be partners, and that would be our conjugate acid. And once again, the only difference there is that one H plus that has basically traveled from the HCl to the water in this particular case. And again, yeah. It is. So we're going to talk about the relationship kind of between them, and it does depend on sort of where they come from. So we'll see it, I think, in a little bit on another slide. But the relationship is this: basically, if the conjugate acid or even the conjugate base comes from something that is strong, it's going to be relatively weak. And if it comes from something weak, it's going to be relatively strong. Strong in the sense of something we don't really talk about too much in this class, but what could happen is if it is relatively strong because it comes from a weak acid or a weak base, the partner on the other side, it has the ability to continue to react with water and affect the pH, for example, of the solution and stuff like that. It's nowhere near like a strong acid or strong base in that sense, but it has the ability to kind of continue to react. If something comes from like a strong acid or a strong base, its conjugate part is going to be relatively weak, which means for the most part, is not going to continue to react with water or anything like that. It's sort of considered a neutral sort of part or a neutral salt, and it really won't do much to affect the pH. Other questions? Hold on. All right. And again, as I was mentioning before, when we do look at a reaction, always our regular old acid and bases on the left-hand side of the arrow and our conjugate partners on the right-hand side of the arrow. And here's just sort of what's happening. Again, the HCl going to transfer that H plus over there, making our hydronium ion and our Cl minus. All right, so why don't you take a moment here? Which of the following represents a conjugate acid base pair and see what you come up with here? Okay, let's take a look. So really, we just want to see is the difference here an H plus, and again, that should be the only difference. Basically, is one of those guys. And in this particular case, the difference is just one H plus. You could either put the H plus back on the guy on the right and on the left, or take the H plus off the guy on the left, you get the guy on the right. So this one is a difference of that. How about this one here? That is a difference of H plus, but there's also a difference of a oxygen. So because it's not, they really aren't each other, so this guy would not be a pair. Looking at the next one here, they are a pair. If we took the H off of here, we're left with HPO4. And once again, when we lose that positive charge, we become one more negative. So that's what I was talking about before, that the charge also changes in terms of that relationship. And here, this one as well. Once again, when we take the H off of here, we're left with NO3. And this is neutral to begin with, but when we lose that plus, again, that then becomes one negative. So it looks like 1, 3, and 4 here are partners. Are these guys partners? These two guys are not partners either, because the difference here is 2 H pluses. And that's because this guy right here is what's referred to as a diprotic acid. It has basically 2 hydrogens that could come off. And by the way, hydrogens actually come off one at a time. So what would happen in this situation is the H2SO4 would lose a hydrogen and make HSO4 minus. Then the HSO4 minus would lose a second hydrogen and become SO4 2 minus. And if we look at the overall reaction, it is basically the H2SO4 making 2 H pluses and sulfate. So although we oftentimes will focus on the overall reaction, for example, but it actually does come off in sort of a stepwise fashion. That is why this guy here and this guy here, they are partners with each other. That is also why this guy here and this guy here are also partners with each other, as the only difference is 1 H plus. But going from here directly to that guy, no good, as the difference there is more than 1 H plus is 2 H pluses in terms of the difference. Any questions on that there? Okay. So although it does come from that thing, it is a little bit different. All right, so for each of these, why don't you write the conjugate base? And why don't you also, for this guy, write the conjugate base and also the conjugate acid. There's pretty much an H plus difference. The question is really, do you put it on or do you take it off, is sort of the important question. So this is why it's important to not drop your pen on the screen, but it is important to think about sort of the relationship that we talked about. We have our acid and bases, and on the other side, we have our conjugate acid and our conjugate base. So in this particular case, remember, an acid is related to the base, conjugate base, and the base is related to the conjugate acid. So in this particular case, we're looking to write the conjugate base, which means if we followed it backwards here, pretty much everything there is an acid, and we just have to go by our definition of an acid, which is something that will actually donate the H plus. So now we've determined that basically we need to take off the H plus in each of these cases. So I'm going to take off the H here. That leaves me an H and an S. And again, when I lose that positive charge, I become one more negative. Taking off the H plus on the second one leaves me just an S. It's already -1, which means that we should end up at -2. Here, taking off an H, it is neutral, which means we'll end up with a negative charge. And here taking off an H will leave us one H and SNO3. And once again, we will become negatively charged in this case. Any questions on that there? All right, so sort of following the same logic here, we got some bicarbonate. And if we're looking for our conjugate base, following back our idea here, we should take off the H plus and end up with CO3 2 minus. Again, the charges do change, so make sure you do not leave them off. If we are going to be looking for the conjugate acid, once again, conjugate acid on the original side there is a base, which means in this case, it's going to accept the H plus, right? And that means that we will end up with H2CO3 in this case. Any questions on either one of those there? Now, this particular guy right here, which is bicarbonate, can act, as you can see, in certain cases as an acid or a base. Those are things which are known as being amphoteric. An amphoteric substance is a substance that can act as an acid or a base. Water is also amphoteric, can act as an acid or a base in certain cases. Any questions on Bronsted Lowry conjugate acid base pairs? So again, most people really screw up on the not getting the charges right here, yes, and not knowing to put it on or take it off. So sometimes, again, it's really helpful to think about it sort of backwards there and what it is. Any questions? Yeah. Yeah, so a lot of times most amphoteric things, not all of them, but most amphoteric things will have a hydrogen still, which means they can still give it away. And usually they'll have like a negative charge, which means they could either give it away or accept it. And those are very common things that can kind of go both ways. For example, like HSO4 minus also, something like that. So usually those are the kind of the key things. Remember, if something doesn't have a hydrogen, there's no way it could kind of give away a hydrogen, right? So it can never be really an acid in that case. Other questions? Okay, then let's talk a little bit about acid strength. So the forward direction of the reaction can also sometimes come backwards, and the products can make some of the reactants, and that's a reversible reaction. Which we usually see arrows in both directions. We also remember to see that when we talked about weak electrolytes. So something like hydrofluoric acid, for example, is a weak acid. It can break apart into H plus and F minus, but these guys could also come back together and come back the other way to make our HF. So that is definitely a weak acid. That is different than something that is a strong acid, which will 100% break apart into H plus and Cl minus. It is a strong electrolyte, which means it will pretty much not stay together and break apart. So let's talk a little bit how we can maybe figure out, is it going to be a strong acid versus say a weak acid? Obviously, strong acids and also strong bases are strong electrolytes, and weak acids and weak bases are weak electrolytes, which means they really do stay together. So one of the big hints is if you do see those kind of reversible arrows, it's going to be either a weak acid or a weak base. But if we do have a strong acid, it will completely dissociate. And obviously, if the reverse direction goes, we'll have a weak acid. So what are some strong acids that you really should know? And that's going to help you pretty much make that determination. Strong acids, that is hydrochloric acid. That is perchloric acid. That is sulfuric acid. That is hydrobromic acid, hydroiodic acid, and nitric acid. So these 6 really kind of strong acids are pretty much your go-tos. Pretty safe bet if it's any acid outside of those 6, it's probably more of a weak acid. So that's a really kind of quick way that you could determine that. So definitely you should know those strong acids as you continue on as well. It'll make your life easier as you get to 1B, for example. Strong bases, as I talked about earlier, pretty much your kind of group. And again, not everybody from group 1 and group 2 on the periodic table that has hydroxide in it. Again, like KOH, sodium hydroxide. Once again, if you kind of look at group 1 and kind of go down to like a potassium is, and then hang over and kind of come down to group 2, any of those guys pretty much with hydroxide is going to be more on the strong side in terms of a base. And again, a lot of strong bases will have actually hydroxide in it. Not all of them, but that's where a majority of them can be found sort of from group 1. And make a right there at potassium and go down to group 2. Will get you a lot of your kind of stronger bases. So as was sort of an earlier question, a strong acid or really even a strong base, its conjugate partner will be relatively weak. And if something comes from a weak acid or a weak base, its partner will be relatively strong. So just to sort of give you an example, for example, if we had like HF, which as we just talked about is a weak acid, when it breaks apart, it's H plus and F minus. So this guy right here is a weak acid, and this would be its conjugate base. And what we mean by being relatively strong is, as I mentioned before, this F minus, when it is created in solution, will actually go and react with water, and it will act as a base and accept an H plus, and it will make HF and some hydroxide. So it's able to be sort of a base, but once again, it is nowhere near as strong as something like sodium hydroxide, which just has to go in to the solution and produce hydroxide. So this is definitely going to be a base. This reaction, by the way, was sometimes referred to as a hydrolysis reaction because it involves water. And it's one of the reasons why certain salts that you produce in an acid-base reaction make the solution acidic, and some salts are basic, and some salts are neutral. So what kind of salts would be neutral? It would be something that came from like HCl, for example. HCl, as we talked about, a strong acid will 100% break apart into H plus and Cl minus. In this particular case, this is our acid, which is a strong one. And this is going to be our conjugate base, which is relatively weak. So why is it weak? Well, when Cl minus is involved there with water, nothing's going to happen. So there's going to be no reaction that's going to happen. So it's sometimes referred to as a neutral salt because it comes from a strong acid. So as I was saying earlier, anything that comes from a strong acid or strong base will be relatively weak as conjugate partner. And anything that comes from a weak acid or weak base will be relatively strong, which really means in this context that it's able to react with water and have a little effect on the pH of the solution. Any questions on that? All right, and in 1B, you'll do calculations of pH and all that stuff with hydrolysis. Fun things. All right, so we had our list there of some strong acids, and we talked a little bit earlier there about our diprotic acid. Obviously, there's also like a triprotic acid, which has 3 hydrogens to give, something like phosphoric acid. Actually has 3 of them that comes off, and they actually do, as we've talked about, come off basically 1 at a time. I'll just go up since I ran out of room. H2PO4 minus will give off an H plus and HPO4 2 minus. And lastly, HPO4 2 minus will lose the 3rd hydrogen and make phosphate there. And obviously we talked about sulfuric acid earlier, which is a diprotic acid, which has 2 hydrogens come off 1 at a time. And this guy right here, which is HCl, is sometimes referred to as a monoprotic acid. Monoprotic meaning obviously it has 1 hydrogen that it could give off. at a time. Is it easier to take away, say, the first hydrogen or second hydrogen when you have like a diprotic or triprotic acid? Which one's easier to come off? It's actually the first one's much easier to come off. That thing's neutral. So when you release the H plus, you now end up with a negative charge. And you're trying to remove something that's positive. It's going to be much harder. Gets even harder as you get down to here. So in the case of something like phosphoric acid, pretty much all the hydrogen that comes off in the first step. The other ones, it's like a super small amount of it keeps coming off. Most of it will come off in that first hydrogen that comes off. Any questions on that there? Yeah. All right, so most acids are oxyacids. Oxyacids is much like the name implies, is an acid that contains oxygen. So our good friend acetic acid, which is a weak acid, or something like, say, nitric acid, which we've drawn before, I think maybe when we did some Lewis structures. If not, this is what it looks like. And in this particular case here, it is actually this part of it that is the acid part. It is this part H that comes off. That's the H plus that actually gets removed to make it an acid. Something like acetic acid has a carboxyl group as its backbone, and acetic acid looks something like this, also known as ethanoic acid. You take organic. This is the carboxyl group. And it is, again, that hydrogen right there that comes off. It is that hydrogen that comes off in both of those cases because, as we talked about with bonding, that OH group is a polar group, which means this is more negative, this is more positive. So this bond is weakened to begin with, right? Because the electrons are heading towards the oxygen is more electronegative. And that's why that hydrogen pops off. That's why none of these other hydrogens over here, in the case, say, of acetic acid, pops off, because those are all non-polar, which means they're sharing electrons equally. It's going to be kind of a little bit stronger of a bond, if you will. Much easier, obviously, to pull off these electrons that are closer to the oxygen, weakening that OH bond, and that's the one that does come off. Any questions on that there? All right, so we talked a little bit about something being amphoteric, and water is also an example of something can be amphoteric. It can act as an acid, as we saw a little bit earlier. It could also act as a base. And as we'll talk about, water can even react with itself, which is what's happening a lot of times. So here's a couple of examples. So in this case, water acting as the acid, so it's going to donate the H plus. And in this case, water acting as the base, which means it will accept the H plus. As I mentioned before, water can even react with itself, where one water acts as the acid, the other water acts as the base. And obviously, we'll just call this guy the acid, this guy the base. So the H plus will come over there. And it will produce H3O plus and OH minus in solution. And that's constantly happening in a water sort of solution. And this is what is sometimes referred to as an equilibrium is set up. This really those reactions heading in both directions. And an equilibrium is what happens in a reversible reaction. And what it means is because there's two directions, when something reaches equilibrium, is actually the rate of the forward reaction, which is going from reactants to products, will equal the rate of the reverse reaction, which is when those products go back the other way. Equilibrium sometimes misunderstood as meaning that you have equal amounts of everybody on both sides, because the word equal is in there, I suppose. But really what it is talking about is that rate. So it's really the rate being equal of it going to the products, and the rate equal as it comes back the other way. So just as fast as it goes one way, it'll come back the other way. And what that essentially does is locks everybody into place, basically, as to where they are in terms of their concentration or pressures. Are you talking about this era versus this era? Yeah, so it's really this arrow that should be there, but I think it's just like a PowerPoint thing. They didn't have that arrow, so we went with that one. But it's basically, it's a reversible reaction. Yeah. Just to show you that one's giving away the hydrogen, one's accepting it. Yeah. Other questions? All right. So what this effectively will do is it will create a relationship because this is an equilibrium, which is sometimes referred to as KW. And KW is the concentration of H plus times the concentration of OH minus. And at 25 degrees, and most of the time that you're doing problems, it will equal 1 times 10 to the minus 14. So again, this is a place where you could use H3O plus or H plus. They are interchangeable with each other. This is the equilibrium constant for water. And the relationship between H plus and OH minus is really an opposite relationship. So as the concentration of H plus increases, the OH minus concentration will decrease, and vice versa, obviously. And by the way, when we have the little brackets, that means concentration. And pretty much that means molarity, as we were talking about. Is pretty much what we're talking about there in terms of that. So we could actually use this sort of relationship to help us decide whether or not a solution will be acidic, basic, or neutral. Basically here, the H plus concentration represents, or the H3O plus represents really the acidic part of the solution. The OH minus here represents the basic part of the solution. So by comparing the concentrations of each of those things, we actually can determine whether or not that solution, again, is going to be acidic, basic, or neutral. 1 times 10 to the minus 14, which is the value of KW, is a number that you should remember and you always have available to you and usually never given to you in problems. Yeah, so you usually have to remember to use it. And again, you would use it to calculate either one of those concentrations. The good news is it is the same calculation regardless of which one's given to you. Basically, you're going to take 1 times 10 to the minus 14 divided by the concentration number that is given to you. The really important part in this chapter is your exponent button. Yes, so you want to make sure that definitely in this chapter you are using your exponent button correctly. Otherwise, you will find yourself off in all these calculations. We're going to be using logs soon and inverse logs. And if you're using that to do scientific notation, you're just going to compound the error that you're going to have. So well, for sure, make sure you use that exponent button when you use it. These type of problems. So if we compare these things and we have a larger H plus concentration than OH minus concentration, the solution will be acidic. If we have a larger OH minus than H plus, which means the basic part is larger than the acid part, it will be basic. And if they equal each other, which means they both will have a concentration of 1 times 10 to the minus 7, then you have actually a neutral solution at that point. And again, this is how we calculate it. Each of them, they're really the same calculation, regardless of which one's given to you. But once again, here, we want to make sure we use our exponent button. Any questions on that there? All right, so let's try some here. Grab your calculator, make sure you know how to do them correctly. Let's take a look at one here, or a couple. All right, these are 4 different problems. So for each of these problems, calculate either the H plus or OH minus, depending on which one's given to you, and determine is it acidic, basic, or neutral. So grab your calculator, make sure you use your exponent button. Make sure you get the right answer, hopefully. Okay, let's take a look. So really, each of these, we're just going to use our KW relationship, which is our H plus concentration times our OH minus concentration. Again, that equals 1 times 10 to the minus 14. So again, it really is sort of the same calculation regardless here. So we'll start with the top one. In this case, we're going to solve for the OH minus concentration, which would be 1 times 10 to the minus 14 divided by our H plus, which is 3.4 times 10 to the minus 4. We once again want to make sure we use our exponent buttons when we punch this in. So 1 exponent button negative 14 divided by 3.4 exponent button negative 4. Negative would be good. There we go. Going to give us a 2.9 times 10 to the minus 11. This needs molarity as it is a concentration here. Any questions? Not one there. Acidic, basic, or neutral, this one. This one is going to be, we're going to compare the H plus, which is the acid part, to the OH minus part, which is the base part. The larger number is which one? It is the H plus, by the way. Yes, so it is acidic. Remember that the negative exponent is important. The negative exponent is important here because -4 means you go 4 places to the left and put zeros, right? But -11 means you're going to go 11 places to the left there and put zeros. So that's a much smaller number. So in a negative exponent, the smaller number is actually the larger value. Yeah. Any questions on that one there? Okay, so looking at the next one there, we are again going to solve for the OH minus, which will be our 1 times 10 to the minus 14 divided by our 2.6 times 10 to the minus 8. Once again, using our exponent button. Going to get us a 3.8 times 10 to the minus 7 molar as our hydroxide concentration. In this particular case, comparing our acid part, which is to the minus 8, to our base part, which is to the minus 7, it is going to be this part that is larger. So that solution should be basic. Yeah. Any questions on that one? By the way, when you are asked that question on this type of problem or future problems, there is only one answer to that. Yes, it should either be acidic or basic or neutral. It should not be like acidic and basic at the same time. Yes, is kind of my favorite answer, but it should not be. Here we're going to solve for the H plus. So we're just going to take our constant 1 times 10 to the minus 14, going to divide it by our 6.2 times 10 to the minus 9. And in this particular case here, going to end up with 1.6 times 10 to the minus 6 molar. And in this particular case, comparing our OH minus to our H plus is larger, which means it should be acidic in this particular case. Lastly, there we have the OH minus, which means we could calculate the H plus. So let's go with this here. So once again, we're going to do our H plus is equal to our 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3, 1 to the minus 14 divided by 8.1 to the minus 3. Going to give us a 1.2 times 10 to the minus 12. Again, needs molarity. And comparing here, our OH minus is definitely larger in this case, which means that it is basic. Any questions on any of those there? If you find yourself with the number that looks very similar, but just slightly off with the exponent, it is probably the way you're putting it in your calculator in terms of scientific notation. Yeah. So if you need help, make sure you come see me. We'll figure it out one more time. So make sure you punch it in correctly. Any questions on any of those there? All right, let's take a look at some more here. All right, let's try this one. We'll do a different problem. Who cares? Let's just do the what is the OH minus here, and is it acidic, basic, or neutral? So here, same calculation. OH minus going to be 1 times 10 to the minus 14. Divided by our 2.8 times 10 to the minus 5. Again, 1 exponent button -14 divided by 2.8 exponent button -5 hit equals. And again, get a 3.8 times 10 to the minus 10 molar. And in this case, again, comparing our OH minus to our H plus, we do see that our H plus is larger in this case, which means that it will be an acidic solution. Any questions on KW, how to calculate H plus? Again, it could also be H3O plus, ROH minus concentration. Again, the important thing is most people struggle with the punching it in correctly. So make sure you got that exponent button going. By the way, your calculator may not always give it to you in scientific notation, right? It may be a decimal form and stuff like that. All right, let's take a look then. We're going to skip this one, I think, and we're going to talk about the pH scale. The pH scale is another way that we measure acidity. pH scale runs from 0 to 7 to 14. Below 7 is acidic. Above 7 is basic. And really 7 on the nose there is neutral. And that's because H plus and OH minus equal each other at that point, and you do get a pH of 7, really. And as you go from 7 towards 0, you become more acidic. As you go from 7 towards 14, you become more basic. And for us in this particular class, and some people have some variations on it, but just to keep it simple for us, if it's not 7, it has to be 7 to be neutral. If it's slightly above 7, they'll be slightly basic. If it's a little bit below 7, it'll be slightly acidic. It's got to be pretty much on 7 for it to be neutral. So to calculate the pH scale or the pH, this is the formula here. There's no negative. The pH is equal to minus the log of the H plus concentration. Once again, you could substitute H3O plus into here as well. So same deal. If you have a display calculator, you punch it in exactly the way it's written. You hit the negative button, not the subtract button. You hit the log button. Then you punch in your concentration using your exponent button. If you have a non-display calculator, you need to go backwards with this one, and all the rest of them we're going to see in this chapter. You got to start with the number, hit log, and then hit the negative button. If you're not sure what type of calculator you have, hit the log button. If it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator. So that is how you determine that now. So display calculators, every equation just the way it's written. If you have a non-display calculator, again, pretty much you got to go backwards. So let's talk about pH and significant figures, which is everybody's favorite, which is the number of decimal places you should have in your pH value or pH-like value should equal the number of significant figures there are in the original solution. So here we're going sig figs to decimal places and vice versa if you're going backwards, which we'll talk about, decimal places to sig figs. So why don't you try one here? We have an H plus concentration of 1 times 10 to the minus 5. Why don't you calculate the pH to the proper number of digits? See what you come up with here. Again, display calculator, type it in exactly the way the equation is written. Non-display, go backwards. Okay, let's start with the calculation here. So we'll take the pH is equal to minus the log of 1 times 10 to the minus 5. And you should get 5 on your calculator, I hope. Yes, that's what you should get. So should we record 5? Should we record 5.0, 5.00, 5.00000? That's a lot of zeros. Might look more scientific, but maybe not. All right, which way should we record it? 5, 5.0, 5.00. So the rule is the number of significant figures in this number is how many? It is 2. That is not how many significant figures you should have. It is how many decimal places you should have. So you should end up with 5.00. So we're going from significant figures to decimal places. And later when we talk about going from pH back to H plus, decimal places to sig figs. So again, not sig figs to sig figs or anything like that. Question on that there. By the way, that would be acidic, basic, or neutral, this guy. Would be acidic as it is less than 7. Yeah, so the pH is less than 7, so it would be acidic here. Any questions on that one there? All right, we'll lay it up there for today.